Okay, let's talk about confidence intervals for regression coefficients. Okay, so this is the definition of a confidence interval. If we use the same sampling method to select different samples and computed an interval estimate for each sample, we would expect the true population parameter, beta 1, to fall within the interval estimates 95% of the time. I'm going to leave this slide up for a second to let it sink in because I think the concept of confidence intervals is one of the most often misinterpreted concepts in all of statistics. Maybe second only to a p-value, although I don't know. I think confidence intervals might get misinterpreted more. The thing that's really important to recognize here is that a confidence interval is a description of the sampling method. And so when we say something is a 95% confidence interval, or we make a statement like we're 95% confident that the value is between X and Y, that word confident has a lot of baggage to it. And this is what we mean by it. And so it does not mean that beta 1 falls between the specific interval that you saw on a given model that you fit 95% of the time. That is not what it means. So for example, if I get a confidence interval for my beta coefficient, let's say I get a confidence interval with a lower bound of 5 and an upper bound of 9, it would be incorrect to say that we would expect the true value of beta 1 to fall between 5 and 9 95% of the time. That is not correct, because that 5 and 9 is just one of the potential computed interval estimates for one sample. And the confidence interval, the 95%, refers to if we were to select different samples and get different estimates for that interval each time, we would expect the true coefficient for beta 1, or whatever beta that we're looking at, to fall within those estimates 95% of the time. So if we did this 100 times, if we select a different sample and compute a new interval estimate 100 times, we will end up with 100 different interval estimates. That interval estimate between 5 and 9 that you see, that's just one of the 100 different ones that we get. So each one of those interval estimates would be different, and we would expect that 95%, so 95 of those 100, would contain the true population parameter for that beta coefficient, and we would expect that about 5 would not contain it. So we don't actually know where our confidence interval with the 9 and 5, we don't know if that is in the 95 or in the 5 that does or doesn't contain the truth. So it's really important when you're describing the confidence interval that this is the way you do it. We expect that true parameter would fall within the interval estimates with an S 95% of the time. So it will not fall between 5 and 9 95% of the time. It would fall between the interval estimates that were calculated using the same procedure that we did on different samples 95% of the time. Okay, so how do we actually calculate it? So this is the formula for a confidence interval where beta hat I is the beta coefficient for a given predictor I. T star is some critical value that we'll get into in just a second. And the standard error of beta hat I is the standard error for that beta coefficient. And so that T star is the critical value from a T distribution with n minus p minus 1 degrees of freedom. And so this n minus p minus 1, we could also write this as n minus, in parentheses, p plus 1. And we want to give it the desired confidence level, which often is 95%. So let's just do this in R. So just as a quick example, I've created a data frame, a data set here where X is my design matrix, where I have a column of ones and then one predictor here. There are 5 observations in this data set, and there is one predictor. And since I have an intercept and that one predictor, I have 2 columns in my design matrix. And then I have 5 values for my Y, or my outcome. So using the formula that you all are very familiar with, X transpose X inverse X transpose Y, we can calculate beta hat. And so my intercept, my estimated intercept is 1.59. And my estimate for beta hat 1 is 0.43. Okay, so now if we wanted to calculate the standard error of beta, and you should be familiar with this because you did this in the lab, I can first calculate my residual, so it's going to be y minus x beta, or y minus y hat. And I can calculate the variance of that residual by taking the sum of those residuals squared and dividing by 5 minus 2. So 5 is my n, p is 1, and then we do n minus p plus 1, so n minus 2. To calculate the variance of beta, we're going to multiply by that variance of the residual times x transpose x inverse. And so because there are two beta coefficients, beta 0 and beta 1, my variance covariance matrix for beta, I would expect this to be a 2 by 2 matrix. And then the standard error for beta, we're going to just take the square root of the diagonal of that variance covariance matrix. And so we end up with a standard error for beta 0, or for our intercept, of 1.8, and a standard error for beta 1, or our slope, of 0.589. And so again, that standard error kind of tells us the variability we would expect between samples if we were to get a new sample. So in this case, I have a sample of 5 observations. So I have 5 x values and 5 y values. And if I were to draw a different 5 observations from that same population and get 5 x values and 5 y values, this is kind of the expected variability we would expect to see if we were to estimate that beta coefficient. So this is what statistics is all about. I mean, all of statistics is sampling and then estimating true values. And so what we're doing is often, if we had the entire data for a certain population, if we had every single observation, we wouldn't need statistics because we could just say what is actually true in that population. But that's really never the case. We are often estimating kind of what we think would happen in a larger population because it's hard to be able to calculate or collect information on every single individual in a given population. And so often we collect from a sample, and then we try to estimate basically how someone else from that sample would look with some kind of assigned variability. All right, so using that formula that we talked about for the confidence interval, we've calculated our beta hat, we've calculated our standard error, so we just need a t-star. So to calculate t-star, we're going to use first the qt function. So q stands for quantile and t stands for the t-distribution. And so what this is doing is it's giving us, it's telling us the critical value of the quantile for the 0.975. So this is we're going to get back to why we're using 0.975 in just a second, but that's giving us the 0.975, or the 97.5th percentile of this t-distribution. And then the second argument of the qt function is the degrees of freedom. And so in this case, it's going to be that n minus p plus 1, or n minus 2. So 5 minus 2. We end up getting 3.18 for our critical value. So that's what we would plug into our confidence interval. Now, why have I plugged in 0.975? I thought we wanted a 95% confidence interval. Why am I using 0.975 instead of 0.95, for example, for the quantile? So it's because we want a two-sided p-value, and this is almost always the case that you want a two-sided p-value. I'm going to show you some pictures to try to help kind of get that point solidified a little bit. So this is a picture of a t-distribution, and this is a t-distribution with 5 minus 2, or 3 degrees of freedom, which is why it looks like this. And I've drawn this line here, this line at the at the 0.95 level, which comes out to be something like 2.3. And so what this means is that 95% of the mass of this distribution is to the left of this line, and 5% is to the right. And so if we're calculating a 95% confidence interval that's one-sided, we would end up with 5% of the mass over here, and this would be what we'd want to use. But often we want two-sided confidence intervals because we don't know for sure if our true value is to the left or to the right of 0, right? We want to see something as extreme or more extreme, and it would be just as extreme to see something on this side of the symmetric distribution than on this side. And so when we're calculating these lower and upper bounds, if we use this value here at 0.95, so this 2.3 approximately, something around there value, then we actually end up with 10% of the mass cut off because we have 5% on this side, 5% on this side, and 90% in the middle. And so if we do a two-sided confidence interval where we use the critical value for the 95th quantile, or the 95th percentile, we actually are calculating a 90% confidence interval because there's only 90% of the mass there in the middle. If instead we fit this confidence interval with, in this case, I've scooted these lines over to be that 3.18, or that value for when I did QT 0.975, now we have 0.25% of the mass on this side and 0.25% of the mass on this side, and we have 95% of the mass in the middle. So that's why we're using the 0.975. So that's an important thing to note here. Okay, so we want to make sure we use 0.975, so we're getting a 95% confidence interval that's two-sided. And my lower bound here is going to be beta hat minus that critical value times the standard error that we calculated. So my lower bound for the intercept is negative 4.22. My lower bound for beta hat 1 is negative 1.44. And then my upper bound is going to be beta hat plus t star times the standard error of beta. And so in this case, my upper bound is going to be 7.39883, or 7.40 if we round it. And my upper bound for beta hat 1 is going to be 2.31. And so here I can just write that out, the 95% confidence interval for beta hat 0 and the 95% confidence interval for beta hat 1. And we can check those results. There's actually a function in R called confint. And so if we fit a linear model here using the lm underscore fit, or the lm function, and I call this lm underscore fit, I can run the confint function on that, and it actually calculates confidence intervals for each of my coefficients. And so I can check that those results are the same, which, flipping back, it looks like they're exactly the same. Okay, so you can also calculate something called a confidence region. And so that's if you want to calculate a confidence region for more than one parameter. So each of these are going to be basically univariate confidence intervals just for the individual beta coefficient. But you could imagine that maybe you want to have a region of confidence across multiple beta coefficients. And so to do that, this is the formula. It's beta hat minus beta. So these can be vectors here. Transpose times x transpose x times beta hat minus beta is less than or equal to p plus 1. So that's the degrees of freedom here, times sigma hat squared times an f critical value where the f has p plus 1 degrees of freedom and n minus p plus 1 degrees of freedom, because remember, f distributions have two sets of degrees of freedom. And this is going to form an ellipsoid region if you do this. So this will form an ellipsoid region. Okay, so I want you to plug this data that I've given here. So I've got a y and I have two x's. I want you to plug this in R, and I want you to fit a model predicting y from x. And I want you to do this quote unquote by hand. And so like in the matrix form where you calculate the variance by hand, you pull out that standard error, you get those critical values and calculate the confidence intervals. And so like I demonstrated here, but with this new data set. So calculate those confidence intervals by hand. And then I want you to check that with the confint function to make sure you got the right thing. And then go ahead and interpret those intervals for each of the beta coefficients. And then as a stretch goal, I want you to try to see if you can figure out how to calculate the joint confidence interval for beta 1 and beta 2. See if you can figure out how to do that. And there's some hints in your book if that, if you want to check that out too. So go ahead and work on this in an RMD file in RStudio Pro, and then knit it and upload the HTML file to Canvas.